Good afternoon, everybody, or good morning, or good evening, whenever it is you're tuning in. So now we're getting to the good stuff. We're getting to um, more biologically active hydrocarbons. Um, Hydrocarbons that you're actually going to find in living organisms like ourselves. And so we get into the more of sort of biochemistry part, which of course, makes me very happy. So we're going to be talking about hydrocarbons that have what we call active groups. These are going to be a lot more biologically active and engage in a lot more biological and non-biological reactions than the saturated hydrocarbons, which are basically only good for burning, and that's about it. But now we're starting to make like really important um, biological molecules like vitamins and hormones and all those sorts of things. So let's just jump in. So we want to recognize there's a bunch of different unsaturated hydrocarbons. We're going to be naming them by the same old system we've been using before. You'll notice that one of the names that's given is olefins. That's a name given to alkenes. Alkenes have double bond, carbon-carbon double bonds in them and are subject to lots of interesting reactions that we'll learn about. We'll look at specific reactions of alkenes because there's a lot of different ones that happen at the point of the double-double bond, the carbon double bond, where one carbon gets reacted with one specific substituent and the other carbon gets reacted with a different one, and we'll see those. And what's really interesting in terms of what I find really interesting in terms of biology is understanding isomers and chirality. Chirality in particular, I'll talk about that at the end of the chapter. Chirality basically means handedness, meaning that one molecule can look like your right hand, and another molecule can look like your left hand. And even though chemically you would think they'd be identical, actually they're quite different. Even though if you wrote down the formula of them, they're exactly the same. I think that's really cool. So let's look at some of the unsaturated hydrocarbons. Three basic ones that we're going to learn about in this particular chapter is alkenes, which have a carbon-carbon double bond, alkynes, which have a carbon-carbon triple bond, and then a really special section of unsaturated hydrocarbons called aromatics. Aromatics are ring structures, typically with 6 carbons, but not always, and they have alternating double and single bonds, and we sort of make a drawing of them that look like that. And we'll learn that they have really special chemical properties, different from the alkenes and the alkynes, which are very, very active chemically. Aromatics tend not to be terribly active chemically because of the very special way these bonds are formed. So let's look at alkenes first. So basically, an alkene is any unsaturated hydrocarbon. And what we call, this is something we're going to be talking about a lot, a functional group. A functional group is basically something that differentiates it from just a hydrocarbon with carbons and hydrogens. It is a group that allows it to be individually specified. It means it has a particular name, and it means that reactions can take place at that particular spot. And so the simplest one is just the alkene with the carbon-carbon double bond. And we call that carbon-carbon double bond a functional group because it is not a typical saturated carbon-carbon bond, and reactions can take place there. Whereas hydrocarbons, saturated hydrocarbons, aren't that chemically reactive. And alkenes are a lot more chemically reactive. The double bond, if we remember, is shorter than a typical carbon-carbon single bond and also stronger. So that sounds a little odd that it's stronger and yet more chemically active. But the point is that it takes more energy to break a double bond. But we'll find out that the reactions that take place with these double bonds, the double bond itself isn't actually broken. Only one, a single bond of the double is broken and the other one stays intact. One of the reactions we're going to talk about, actually sort of a whole group of reactions, are called addition reactions. And just like I said, you have a carbon-carbon double bond, and when an addition reaction takes place, this bond is broken and replaced with, let's say, hydrogens, but this one stays. So even though it is stronger than a single bond between carbons, and it takes more energy to break both of them, for these addition reactions, both of them aren't broken, just one of them is. So that means that alkenes are more reactive than the saturated alkane. So let's look at some biological examples. Terpenes is a whole group of biological molecules that have multiples of 5 carbons in them. And some of the common ones you've probably heard of. You've heard of beta carotene, hopefully. You've heard of limonene and pinene. These are all molecules that you find in fruits and vegetables that give them a particular color or particular scent. And we'll talk more about limonene in a little while because it's a fascinating example of handedness. Cholesterol, testosterone, estrogen, they're all synthesized from terpenes. So these unsaturated double bonds are used as elements to do reactions. And so these simple molecules are built upon by a whole bunch of biological reactions to build these really large, complex molecules. So we start with a simple carbon-carbon double bond, and then through a whole bunch of biological reactions, we build these great big molecules. So these are what they look like. So this is what you see. Beta carotene is huge, big long molecule, and these series of double bonds, you can see there's every other carbon is double bonded. We call those conjugated double bonds. And what that means is that if you get an electron added, it can skip right down that chain of double bonds. And that's what actually happens with beta carotene. We get an electron adding to one end, and it goes flying down the other end through these double bonds, flipping them as it goes till it gets to the other end. So this is pinene. It's a relatively small molecule, and you find that in like rosemary and the really strong scent. And then limonene, as I mentioned, we'll talk about that in a little while because it's just a fascinating biological case study. So the next group are alkynes. And in biology, we don't really see alkynes very much because they're super reactive. So now we have a carbon-carbon triple bond. And so here is a biological molecule with carbon-carbon triple bonds, but it's a toxin. So that's one of the reasons why these things are toxins is because these ends of the molecule are super reactive. And so these poison tree frogs have this in their skin, and the bright colors basically tells their prey that you don't want a piece of this, man. And so they have these really strongly reactive molecules in their skin that if somebody eats them, they get like super sick or die. And so, like I said, they're even more reactive than alkenes. And because they're so reactive, we don't really find them a whole lot. There are some examples, obviously, but you don't find them nearly as much as you do with alkenes. Now we get to the aromatics. And the aromatics, like I said, are a really special subset of unsaturated hydrocarbons because they have really interesting chemistry. Now, they're called aromatics for a fairly straightforward reason. They have a really strong smell. You can smell these things from quite far away. That's why they're called aromatics. Now they have a cyclic or cyclic, depending how you want to talk about it, structure that can be represented like this, where you have alternating double bonds, one here, and then one there. And then if you were to write the skeletal structure, it would look like this. And this is the simplest aromatic. This is called benzene. You probably heard of benzene. So there's benzene down there. When it's part of a structure, when it's attached to something, we call it a phenyl group. Phenyl is just an old name for benzene. Before it was called benzene, it was called phenyl. So we still use that name group. So when it's a group attached to something, we call it a phenyl group. Now the interesting thing, one of the interesting things about aromatics is that if it was a ring of alternating double and single bonds, you would expect that the carbon-carbon single bonds would be longer than the carbon-carbon double bonds, which we know to be shorter. But if we look at the actual length of the carbon-carbon bonds, they're all the same length. And what we call that is a bond order. A bond order of 1 means you have a single bond. A bond order of 2, so there would be 1. Bond order of 2 would mean you have a double bond. Well, benzene is special in that it has a bond order of 1.5, meaning it's right in between a single bond and a double bond. And that's because this bond character moves around. These electrons in the double bond just scoot around the ring. And so we say that they're basically shared equally by all 6 carbons. And so they're constantly moving. We say that they're delocalized. They're not local to any one particular carbon, but they're shared by all of them. And that makes benzene and other aromatic rings resistant to reactions. Most reactions that would break a typical double bond will not break benzene, because the reactions that can break double bonds basically keep those 2 electrons in the double bond in one place and then performs a reaction on them, whereas benzene doesn't have that. Those electrons are in constant motion, and so they really can't be grabbed very easily by anything trying to do a reaction on it. So it makes them very resistant to reactions. They're unusually stable, as I mentioned. And so these, because all 6 carbons are sharing those electrons evenly, we call that a resonance hybrid. What does a resonance hybrid mean? Well, a resonance structure is like 2 different ways to write the same bonds. And so with benzene, we can write the double bond here, here, and here, but we could also write them here, here, and here. It would be the same structure. And in fact, each of them are equally likely. And so the way that most chemists write it is like this: 1, 2, 3, 4, 5, 6, and then just with a circle in the middle, which indicates that all of these carbons are the same. We don't have single bonds, we don't have double bonds. We have a bond order of 1.5, and they're all equivalent. These rings can also fuse together, and we call these polycyclic aromatic hydrocarbons, or PAHs. And so here's a couple. These are found to be in tobacco smoke, and some of them have been found to be carcinogenic. They're also found in mothballs. Mothballs have these, you get that, if you've ever been around mothballs, they have that very special aroma that comes from them being fused aromatic rings. And moths don't seem to like it very much, and so keeps moths away from your clothes. You find them a lot in pharmaceuticals and a whole ton of organic compounds. So here we have a whole bunch of different, what we call functional groups. Here's ibuprofen, and here it's got an aromatic ring. It has a unsaturated alkane portion, and it has an acid portion as well. And then here is epinephrine, which is basically the adrenaline that you find in your body, or you can get it in an EpiPen. It has an aromatic alcohol. We call this a phenol. We'll learn about that in a minute. An aromatic ring, a benzene ring with a hydroxyl group on it. These are the hydroxyl groups. We call that a phenol. It also is an alcohol because it has a hydroxy group attached to a carbon, and it has an amine. We'll learn more about these functional groups in the next chapter when we talk about organic molecules with oxygen, sulfur, and nitrogen in them. But the point of this is you're going to see aromatic rings in a whole ton of organic compounds, biological compounds, pharmaceutical compounds. So how are we going to name these things? So if we have unsaturated hydrocarbons, we basically have to give that information in the name. So we call it an alkene when we have a double bond. And you notice that when we have a double bond, we take away two of the hydrogens. And that makes sense because if we have single bonds between the carbons, then we have two more hydrogens than if we were to put a double bond there, which eliminates two of the hydrogens. So an alkene is going to have two less hydrogens in it than an alkane. And an alkyne with a triple bond is actually going to have two less than that because we've basically removed all. So these would be attached to other carbons. So these two carbons now have no hydrogens attached to them, where there used to be four. With an alkene, then there was two, and then with an alkyne, there's none. So an alkyne with a single triple bond would be C to the N, whatever N is, 2, 3, 4, 5, 6. We multiply that by 2 and then subtract 2 for an alkyne. We just double it for an alkene. So C8H18 would be an alkene. And C8H18 plus 2 is 20 would be an alkane. Okay? So the rules are the same as with alkanes. We look for the parent chain that's the longest, but also contains the double bond. So that part is a little bit different. So we might be able to find a longer chain, but all single bonds. But if there's a double bond in there, that takes a preference. We have to, because it's an alkene, we have to find that chain with the double bond in it that's longest. Then we end in ene. With alkanes, we always end it in ane, methane, ethane, propane. Now we're using propene, ethene, and so on. That just tells us that there's a double bond present. If there's more than 4 carbons, we also have to say where the double bond is. If there's only 3 carbons, 1, 2, 3, well, then the double bond is either there, and we say that that's carbon 1, or it's there and we say that's carbon 1. We just make the assumption that's carbon 1, so we don't have to name it. But if there's 4 carbons, then the double bond could start either at carbon 1 or carbon 2. So we have to say so. And then substituent names are the same names as alkanes, with you have to give them their number. So first would be the substituent, say where it is, and then second would be where's the double bond ending with -ene, okay? Alkynes, let's talk about alkynes for a minute. And we'll talk more about how to name those when we do the review on Tuesday. So a lot of these molecules, especially the smaller ones, have simpler common names that we just use, like acetylene. Acetylene looks like this. Its actual proper name is ethine because it's got 2 carbons, ethane, and it's got a triple bond in it. So we changed the ane to an ine. But for the longest time, it's just been called acetylene, and that's basically the common name for it. You'll find very few people using the term ethine, but that's its actual proper name, and that's the one that we'll use too. Now, aromatic hydrocarbons have, as I mentioned, that special shape. Almost always 6. Almost always a ring of 6 carbons. And like I said, we generally represent it like this, with a ring in the middle. Not always. Sometimes or most of the time it's represented like that, but you'll also see it like this. So as I mentioned, all the carbon-carbon bonds are the same. They don't have single bonds. They don't have double bonds. They have a weird bond and a half kind of arrangement because those electrons that would be in the double bond are shared equally by all 6 carbons. And so we have a bond order somewhere between a single bond and a double bond. It's stronger than a single bond, not as strong as a double bond in terms of how close the carbons are together. So these are some of the representative aromatic compounds, and I will draw some of them for you. So these are ones that you see a lot in organic chemistry. The first one is called aniline, and a lot of dyes, drugs, and resins, and all sorts of perfumes and things start with this, and it is just your benzene ring with an amine group, or NH2, hanging off it. So that is aniline. Next is benzoic acid, which is, again, same thing, but with an organic acid. And we call this a carboxyl group. We'll be talking a lot about that in the next chapter. That is the acid group on acetic acid, formic acid. All the organic acids have this particular, and they're weak acids too. So with benzene, the root is benzene and oic acid, and so this would be benzoic acid. And it's used in preserving food, all sorts of different chemical structures. Bromobenzene, that would just have a bromine there. So bromobenzene is a starting material for synthesis of all sorts of things because it's basically fairly easy to move this bromine out of there and replace it with something else. So it's difficult to get benzene to be chemically active, but if you can get a substitution on it, then you can change that substituted carbon fairly easily. You can get rid of this and replace it with something else. So bromobenzene is basically a starting point for a lot of reactions. And then a really one you'll find a lot. Oh, nitro, that's a good one to have because that's a nitro group, because you remember nitric acid has a nitro group on it. And so one of the nitro group is what we call an electron withdrawing group, because it has nitrogen and oxygen there, which are both highly electronegative. So basically what it does is it pulls those shared electrons on the benzene ring towards itself, and then lends to a lot more reactions being possible. Next is phenol. Phenol is hydroxy benzene. It just has the hydroxyl group on it. And that smell that you find in hospitals, that that sort of that disinfectant smell, that comes from phenol. It is particularly good as a disinfectant because it basically disrupts a lot of biological membranes and that sort of thing. So it basically wipes out viruses and bacteria and basically anything with a membrane in it. And so it's really good at just basically wiping out everything. It's something you wouldn't want to get on your skin. It burns pretty badly. And then finally, we have toluene. Toluene is just methyl benzene. And you may have heard of toluene, even though you may not think so, because when we have a nitro group here and a nitro group there, and a nitro group there. Actually, no, I put them in the wrong place. 1, 2, 3. There we go. Here's my 3 nitro groups. 1, 2, 3. When we have 3 nitro groups there, we have tri-nitro toluene. And you've probably heard of that. Yeah, like I said, nitro groups are electron withdrawing groups. And so they make the benzene ring a lot more chemically active. And if you have 3 of them on a benzene ring, they're basically pulling those electrons away and making it like taut, like the string on a bow. So basically they are pulling the bowstring, and then when you let it go, boom. So that's why TNT explodes like it does, because you have so much strain on that ring of those electrons being pulled away from the benzene ring, that when it finally put a spark on it, the thing will just go boom because of all the strain on that ring. So this is something we should learn about, how you can name different positions when you have 2 substituents on a benzene. So these are all dichlorobenzene. We would call this one 1, 2, because you always give the lowest. Remember, 1 is always the lowest number you can give. So the first one, doesn't matter where it is, just name one of them 1, and then the other one you give the next number. So that would be 1 and 2. This would be 1, 2, 3. And this would be 1, 2, 3, 4. So 1, 2 dichlorobenzene, 1, 3 dichlorobenzene, 1, 4 dichlorobenzene. We also have another name for them, for the positions. We say that these 2 chlorines are an ortho, meaning they're right next to each other. So they're on consecutive carbons. These 2, we would say they're meta. Whoa, meta, man. Means there's 1 carbon in between. And then para means they're on opposite sides of the ring. They're as far away from each other as they can possibly get. So they have three different names: ortho-dichlorobenzene, meta-dichlorobenzene, para-dichlorobenzene. So either name is fine. So we use those when there's two substituents on the ring. Not when there's just one, and not when there's three or four, but when there's two, we tell basically how far they are apart from each other. Let's look at some of the reactions. So they basically all fall under the sort of the larger category of addition reactions, because we're going to add something that breaks that double bond, breaks one bond of the double bond, and then adds substituents to it. So at points of unsaturation, basically where there were a space for substituents, but now they've been replaced by double bonds and triple bonds. So those electrons, which could have been shared with other things, are now just being shared between the carbons. So one of the easiest ones is hydrogenation. So you have a double bond, you basically pump hydrogen in, generally in the presence of a catalyst. So like nickel or platinum in particular. Platinum can dissolve a lot of hydrogen gas on its surface. And so if you have a high local concentration of hydrogen gas on the surface, that tends to speed the reaction along. And so hydrogen will come in, break one of those bonds, and then replace the double-double, feel like I'm ordering from In-N-Out, the double bond with a pair of hydrogens. And we just call that hydrogenation. And this is actually how hydrogenated fats are actually made. You take an unsaturated fat in the presence of platinum, and you pump in a bunch of hydrogen, and all the places where there are double bonds, they get popped, and then you add a hydrogen on one side and hydrogen on the other side where there's a double bond, and then you make fully saturated fats. So you go from a liquid to a solid just by adding hydrogen. Another addition reaction is hydration, and you can probably imagine where this comes from. Hydration meaning water. You're adding water to the double bond, and so it reacts where you have the OH on one side and a hydrogen on the other. So here we have acetylene. We would have a hydroxyl going on one spot and a hydrogen going on the other spot. And that would produce ethanol. And again, we're going to talk more about alcohols and ketones and ethers and all that kind of stuff in the next chapter. We generally need really strong acid for this to take place. It won't take place. You just have ethylene and water together. They're not going to mix. They're not going to react with each other. But if you have a really strong acid, that basically forces that reaction to take place. We'll also be talking about aldehydes and ketones next. That's where we have carbon-oxygen double bonds. We're talking a lot more about those too. So there's something special about the hydration reaction that a Russian chemist named Vladimir Markovnikov noticed about 150 years ago. He was doing these addition reactions in his lab, and he noticed something strange. He noticed he always got a certain product when one carbon had a different substituent pattern than the other carbon. So if you have something like ethene, each carbon is the same, right? One carbon is identical to the other one. They're both double bonded to the other carbon, and they both have two hydrogens. So you can't predict which carbon is going to get the hydrogen and which one is going to get the hydroxyl group. And it really doesn't matter because you can just flip it back and forth anyway. It makes no difference. But What Markovnikov noticed was that the carbon that had more carbon groups attached to it always got the hydroxyl group. So this carbon is attached to a methyl group and a hydrogen. The second carbon is only attached to hydrogens. And so the carbon that has more methyl, ethyl, just basically more carbons attached to it, always gets the hydroxyl part. And the carbon that has more hydrogens attached to it just picks up another hydrogen. That always takes place. And that is known as Markovnikov's rule. And so we can predict if this is an asymmetric molecule. Basically, it's not completely symmetrical, where each carbon is exactly the same. We basically know how the hydration reaction is going to take place. And so synthetic chemists take advantage of this all the time. If they want a hydroxyl group in a particular place, they will always make sure that the carbon that they want the hydroxyl group to go has more carbons attached to it. And if it doesn't, they'll force it and make sure that it does in order to get that hydroxyl group there. All right, I'm going to pause here and pick it up again in part 2.